The 17th century, a period marked by profound change and discovery, a time of exploration and revolution, where the boundaries of the known world were constantly expanding. Telescopes revealed a cosmos far grander than ever imagined, opening up new realms of possibility. Yet a fundamental question baffled even the greatest minds of the era. What was light? It was a clash of titans, a battle of ideas that would shape the course of science for generations. On one side stood the proponents of the particle theory, envisioning light as a stream of tiny particles, each carrying energy. On the other side stood the wave theorists, imagining light as a disturbance spreading through an invisible medium like ripples on a pond. Understanding the nature of light held the key to unlocking the secrets of the universe, from the smallest particles to the vast expanse of space. How did light travel from the distant stars to our eyes, crossing the void of space? What was its relationship to color and vision, and how did it interact with the world around us? The stage was set for one of the most epic duels in the history of science, waves versus particles, a debate that would echo through the halls of academia. The outcome of this battle would determine the direction of optics for centuries to come, influencing countless discoveries and innovations. Little did they know the universe held secrets far stranger than either side could have imagined, mysteries that would challenge their very understanding of reality. The stakes were high and the debate was fierce, with each side passionately defending their theories and seeking to uncover the truth. Among the early champions of the wave theory were Christiaan Huygens and Robert Hooke, two brilliant minds of the 17th century.
Huygens, a Dutch polymath, was a master of lenses and telescopes, constantly pushing the boundaries of what we could see and understand.
And I, Hooke, an English naturalist and experimentalist, was a pioneer in microscopy, revealing the hidden details of the natural world.
Both Huygens and Hooke were drawn to the elegance and explanatory power of the wave theory, which offered a new way to understand light.
In my treatise on light, I proposed that light waves were analogous to sound waves, traveling through a medium in a similar fashion.
I observed intricate patterns of color in soap bubbles, which I attributed to the interference of light waves, a phenomenon that fascinated me.
Together, Huygens and Hooke, through their meticulous observations and experiments, laid the foundations for a wave-based understanding of light, challenging the prevailing particle theory. Their ideas, though radical for their time, would inspire generations of scientists to come, paving the way for future discoveries. But their path would not be easy, as they faced significant opposition and skepticism from their contemporaries. A formidable challenger was about to emerge, casting a long shadow over the wave theory, and his name was Isaac Newton. As Huygens and Hooke built their case for the wave theory, Francesco Maria Grimaldi made observations that challenged both sides.
Grimaldi, found that light did not always travel in straight lines. Instead, it bent and spread out slightly, creating faint fringes of light around shadows. This phenomenon, diffraction, defied easy explanation by either theory.
Grimaldi believed light particles could interact with each other and with the edges of objects. But his observations planted seeds of doubt about the simplicity of the particle model. Diffraction hinted at a complexity in light's behavior that neither theory could fully grasp. It was a tantalizing clue, suggesting that the true nature of light was far more nuanced. Grimaldi's discoveries added another layer of intrigue to the debate. The universe was not about to give up its secrets easily. Robert Hooke saw in the phenomenon of color evidence supporting the wave theory of light.
I noticed that colors of soap bubbles and thin films change depending on the viewing angle. This suggested that color was a result of the way light interacted with objects.
Hooke proposed that different colors of light corresponded to different wavelengths.
When white light struck a thin film, some wavelengths were reflected more strongly, giving rise to the observed colors.
Hooke's ideas about color challenged the prevailing view that colors were inherent qualities of objects. His insights would later form the basis for our modern understanding of color vision and spectroscopy. Yet a new challenger was about to step onto the stage, casting a long shadow over the debate. In the late 17th century, a young Isaac Newton turned his attention to the enigmatic nature of light.
My interest in optics was sparked by my fascination with lenses and my desire to improve telescopes.
He began a series of meticulous experiments, documenting his observations and developing new techniques.
I was cautious about embracing either the particle or wave theory of light.
He was intrigued by light's straight-line travel, suggesting particle-like behavior, yet aware of Grimaldi's diffraction experiments, hinting at a wave-like nature.
I embarked on a quest to unravel the mysteries of light using rigorous methods.
His journey would lead to conclusions that would shake the foundations of optics and spark one of the greatest scientific rivalries. In a darkened room at Trinity College, Cambridge, Isaac Newton performed an experiment that would alter our understanding of light and color. This groundbreaking experiment would become one of the most famous in the history of science.
I allowed a narrow beam of sunlight to pass through a glass prism, projecting a spectrum onto a white screen. The room was filled with an array of colors, each one distinct and vibrant.
To his astonishment, the white light was separated into a dazzling band of colors. This was a revelation that challenged existing beliefs about light.
This phenomenon, known as dispersion, provided crucial evidence for the complex nature of white light. It was a pivotal moment in the study of optics.
Newton meticulously studied the spectrum, measuring the angles of refraction for each color. His detailed observations and calculations were groundbreaking.
I showed that each color of light was refracted by a different amount. This was a significant discovery that would change the way we understand light.
This discovery shattered the long-held belief that white light was pure and fundamental. It opened up new avenues for scientific exploration.
I demonstrated that white light was a mixture of all the colors of the rainbow. This was a revolutionary idea at the time.
Newton's prism experiment propelled him to the forefront of optics, making him a leading figure in the scientific community, and set the stage for a bitter feud with Robert Hooke, a rivalry that would become legendary in the annals of science. News of Newton's prism experiment and his radical conclusions quickly reached Robert Hooke.
I was initially skeptical of Newton's findings.
Hooke publicly challenged Newton's interpretations, arguing that Newton's experiments did not necessarily disprove the wave theory.
I suggested that Newton's observations could be explained by assuming that white light was a simple pulse modified as it passed through the prism.
Newton, fiercely proud of his work, was incensed by Hooke's critique.
I considered Hooke's comments a personal attack and a deliberate attempt to undermine my discoveries.
Thus began a bitter rivalry between two brilliant minds, fueled by ego, ambition, and fundamentally different views on the nature of light. The rivalry between Newton and Hooke, ignited by their conflicting interpretations of light and color, would escalate for decades.
Their feud transcended mere intellectual disagreement, becoming deeply personal.
Hooke used his position to publicly criticize Newton's theories.
Newton, sensitive to criticism, often reacted with hostility.
He accused Hooke of plagiarism, claiming Hooke had stolen some of his ideas.
The rivalry had a chilling effect on the progress of optics.
It discouraged open dialogue and collaboration, hindering the search for a unified understanding of light.
The personal animosity between Newton and Hooke delayed the acceptance of wave theory for generations.
Amid the heated debate, Christiaan Huygens was putting the finishing touches on his treatise on light.
Published in 1690, Huygens' treatise presented a comprehensive exposition of the wave theory.
He explained how light waves propagated through the luminiferous ether.
Huygens addressed optical phenomena, including reflection, refraction, diffraction, and double refraction.
He proposed an explanation for polarization, suggesting light waves vibrated perpendicular to their direction of travel.
Despite its clarity, Huygens' treatise was overshadowed by the Newton-Hooke feud.
The scientific community was hesitant to fully embrace either theory, and Huygens' work awaited a more receptive audience. In 1704, a year after Hooke's death, Newton published his seminal work on light and color, Opticks.
This treatise solidified Newton's position as the preeminent authority on optics.
Newton presented his corpuscular theory, arguing that light was composed of tiny particles.
He detailed his experiments with prisms, lenses, and mirrors, providing compelling evidence for his theories.
He explained reflection and refraction in terms of interactions between light particles and matter.
Newton's optics marked a turning point, shifting opinion in favor of the particle theory.
Newton's prestige and the elegance of his arguments held sway over the scientific community.
His work cast a long shadow over the field of optics for generations.
With Newton's optics and his authority behind the particle theory, the wave theory seemed destined for obscurity. The scientific community, swayed by Newton's arguments, gradually abandoned the wave model. Huygens's treatise languished in obscurity, overshadowed by the Newtonian paradigm. The wave theory, however, was far from extinguished. It retreated, gathering strength for its eventual return. The seeds of doubt sown by Grimaldi's diffraction experiments lingered. The stage was set for a future resurgence, when new evidence would challenge Newton's dominance and spark a renewed debate about the true nature of light.
If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together.